class of by Cindy Regal, where I think when it was Wednesday, he started to talk about quantum mechanics. The second lecture was yesterday on quantum transduction, and today she will do the final lecture of ultracold atoms from QX space.
Great, thanks. All right. So, in terms of where we are, Anna Maria already said basically the idea here. But before maybe the volume is not large enough. Before I jump into the subject of the atoms from the qubit perspective, I wanted to review a little bit some of the references that I put up for the last lecture. So, if you weren't here at the other lectures, I'm an experimentalist over in Gila, and first day we talked about quantum optimum mechanics, and then yesterday we talked about quantum transduction. One of the sort of ways that we were able to quantify what was going on was this idea of input-output theory. And this first paper up here is sort of a classic New Zealand, Australia quantum optics paper that has a title that doesn't sound like input-output theory, but really sort of goes through it in what I think is a compact and useful terminology. The second paper is some of the proposals for how you think about the transduction between the electrical and optical domains, sort of in the way that we were talking about it, in terms of ultimately in the equation sort of eliminating the mechanical mode and thinking about it continuously as opposed to a swap into the mechanics and out again. This other paper is, if I did want to think about my lithium niobate modulator and how well that could work in a quantum limit, this paper by Man-Kei Tsang actually goes through that, and that's useful. And this paper here is from our group, and that sort of goes through the math and results that we have so far on this electro-optic transducer. Any lingering questions from yesterday? Okay. All right, so what we're moving on to, and I gave a preview of this last time, is talking about neutral atoms. From the perspective of my lab, it sort of corresponds to cooling degrees of freedom, motional degrees of freedom, instead of nanomechanical objects, individual atoms. And today what I thought I'd start doing is talking about ultracold atoms from a sort of much broader, a little bit more historical perspective, and sort of seeing how that segues into controlling individual neutral atoms. Then we'll talk about the Hongel-Mandel effect with atoms, and then some examples of creating a Bell state with neutral atoms. So one thing to keep in mind for this talk is that neutral atoms, sort of from this qubit perspective, are much less developed than, say, ions or superconducting qubits. And so the techniques that we're using in the experiments that we're doing, you can sort of backtrack 20 years to what trapped ion people were doing then, and that's sort of what we're doing now. And so if you're still trying to latch on to what experiments do and what is a simple way of thinking about things, well, this is your chance, because I'm talking about sort of the simplest ways that I could characterize entanglement in these type of systems. But I thought it was still worthwhile to go through. All right. So ultracold atoms, the field is sort of grounded in experiments that happened sort of in the mid-1990s, where people were able to laser cool samples of neutral atoms, where that corresponded to, in contrast to ions, many atoms in some trap. And you could cool either bosons or fermions, okay? So the atoms themselves could be bosonic or fermionic. And if you cooled them low enough so the de Broglie wavelength was on order of the interparticle spacing, then you could see momenta distribution that looked like this. And this is a really old cartoon of sort of the classic technique for doing this, which is you have a bunch of atoms, and they're in some bowl potential trap. It has a finite depth, and so you evaporate out the hottest atoms, you leave the coldest atoms, and you have this bulk sample. And this is really what the field was doing for quite some time, is looking at macroscopic properties of these bulk gases of atoms. The field sort of moved on from these dilute gases of bosons or fermions to looking at stronger interactions, or the ability to tune interactions in the system. So you can use what's known as a Fano-Feshbach resonance to vary the scattering length of the atoms as a function of magnetic field. And this allows you to do things like make molecules from the atoms. I think Junier will talk a bit more about that. Make weakly bound pairs from fermionic atoms that effectively act like Cooper pairs. And optical lattices also appeared as a way that effectively you could add strong interactions to the system, in the sense that the on-site interaction in one of these, say, lattice sites could be quite large. And so there's a lot of experiments where you use counterpropagating laser beams that make a periodic potential, and in that way you can also study systems that are periodic and hence represent a little bit more of what one sees in condensed matter. Now, some of the even more recent developments in the field have been trying to look at these ultracold atomic systems sort of from a single atom perspective. So if you make a superfluid and you actually undergo a superfluid to mod insulator transition, and then you look at that spatially in a way where each of these boxes corresponds to where there could be a single atom, then you're able to actually resolve single atoms with a microscope. That picture up there, it maybe looks blurry from the back, but every single one of those dots is just a single atom that you're actually observing. And so these green dots are bosonic atoms in Marcus Greiner's experiment at Harvard. And they can do things like what they call cookie cuttering, where they take this sample that has low entropy, and they actually get rid of these atoms over here, and then they give themselves a line of single bosonic atoms. And so that's one approach that people are using in order to get sort of a more single qubit perspective on neutral atom systems. Now, another idea that has emerged is a little bit more along the lines of trapped ions, in the sense that, well, can we just grab onto single neutral atoms to begin with? And we know we basically have a sort of single atom source, and then can we control that single atom source well enough that we can do something interesting with it? And I have a paper up there on the left. That's some of the very early experiments with this were the early 2000s, where experimenters would take an optical tweezer trap, like that diagram up there, and you just simply put this into a magneto-optical trap, and you can grab onto single atoms. And more recently in Paris and at Harvard, they've been taking the sort of randomly gathered single atoms that are these little dots in this picture, and then they move them around to create an ordered array. This is in 2D, and then these experiments here, you can see it's randomly filled on this top plot, and then they actually move them in real time while they're holding onto them to make this ordered array down here. And we'll talk a little bit more later about what's going on there and how that's actually done. But each of those dots is really a single atom, sort of in the spirit of ion trap experiments. Okay. So as an outline of what I'll talk about, a lot of what I'll talk about is now how do we introduce an interesting interaction between these atoms that we've sort of gathered from the bottom up. Can we control them well enough? Can we, say, entangle them? And so I'll talk first about some of these ideas of how we actually grab the atoms, how we make our single atom source, how we bring many of them together. I'll talk about some experiments that we do specifically in our group, trying to ask that in this particular platform, can we control the motional state of those atoms? I'll talk about an analog to the Hongel-Mandel effect with our bosonic atoms instead of with photons. And that's interesting from the perspective of, if you think of your favorite interesting experiment you might want to do with single photons, there might be some pathway in which we could actually do this with bosonic atoms. And then I'll talk about creating entangled Bell states and characterizing them. And I'll present 3 different ways to give you a flavor of different options. Redburg Blockade I'll mention briefly. We don't do this in our lab, but I think it's probably the most probable way that people will actually do 2-qubit gates in this type of system. I'll talk about spin exchange, and then also how we can use the interference, Hongel-Mandel interference plus measurement, in order to get entanglement. So this is sort of an analogy to a photon experiment. And like I said before, if you're still trying to grasp sort of what are the basic ways that experimentalists get a handle on their system, I will present to you the simplest ways in which one does this that sort of are what ion trappers were doing 20 years ago. So it's a good way to learn about those things. All right. So I think even before I begin, I was going to maybe just give you a little bit sense of the atomic structure that's relevant here. I mean, you guys had to talk about ions, right? And so you probably learned a little bit about what are the qubit states and what are the internal states that are relevant. But let me just draw out the particular alkali atom that we use, and just to give you a sense of, okay, what internal spin states do we actually use in these experiments. So in our experiment, we use rubidium-87. So this is actually the bosonic atom that was actually first cooled to Bose-Einstein condensation. And it turns out to be useful from a perspective of convenient wavelengths and just convenient scattering properties and a pretty simple atom to use. So what does its structure look like? So here. Okay. We have the ground state here, which is the 5s 1/2. And then we mainly use the excited state. That's the 5p 3/2. Okay. And in the ground state here, we have hyperfine structure. And for our atomic physics lesson of the day, we have in the ground state here, we have the total angular momentum for the electron is 1/2, and the nuclear spin for rubidium-87 is 3/2. So we can either have F equals 1 or F equals 2. And the splitting between those two states is 6.8 gigahertz. Okay? And so when we talk about an effective spin system in our experiments, we use basically a hyperfine qubit. So we use one of the Zeeman sublevels of F equals 1 and one of the Zeeman sublevels of F equals 2. So we actually use we'll call spin up is F equals 2, MF equals 2. And then our spin down is F equals 1, MF equals 1. Okay, so these are convenient because they're the stretch states. They're actually it's a magnetically sensitive transition, so that's not so great. It's not a clock state, but it works for these experiments. Okay, so those are the effective spin states that I'll pretty much always refer to as just the up and the down. And the excited state up here, just for good measure, we have J equals 3/2, and obviously I is still 3/2, so we can have F prime equals 0, F prime equals 1, F prime equals 2, and F prime equals 3. Okay, so that's our basic atom, and we'll be driving optical transitions here and using these two guys as our spin. All right, so how do we grab onto these guys? So this is a picture of some of the experimental components. So this is a picture of some of the optics and a lens that actually traps the atoms and some magnetic field coils. That's a picture up there of a glowing magneto-optical trap. So it's about 1 million to 1 billion atoms that this particular transition over here that we use is at 780 nanometers. So you can sort of barely see it, but if you use an IR-sensitive viewer, then you can see this glowing pink ball in the lab. And the experiments in which you grab onto these single atoms are beautifully simplistic in the sense that we take some light, we put the light through some acousto-optic deflectors that deflect the light, so that allows us to actually move the beam, just like an optical tweezer experiment you might see in soft condensed matter. And we can move it in X and we can move it in Y. We can also put multiple radio frequency tones into those deflectors, and that allows us to create multiple traps. So that's the picture you're seeing before of the sort of single string of atoms in a row corresponded to putting different frequencies into AOs like this. Then we just take that light, we put it into a lens, and we focus it down to make traps. And right now, in our experiments, one of the things we've tried hard to do is make the trap waist really small, so 0.7 microns, and that allows us to get enough confinement to do the cooling that we want to do. And so the traps that we can make at this point with these tweezers, we can make a 10 by 10 array of traps. This is just a picture of the traps, or some average pictures of atoms in the traps. So in principle, it's quite scalable in terms of the number of traps. These particular traps are separated by about 1.5 microns when we image them.
So
Yeah.
You have 100 sites?
Yep, we have 100 sites. Yep. And that was it took a while to get enough optical power to get 100 sites, but we have that now. Okay. All right, so what one has to do in order to really sort of have a single atom source is to, yeah.
One quick question, the 0.7, was it like one lattice side or the whole trap?
So the 0.7 is the size of the trap. So the trap itself is a Gaussian focus, and it has a characteristic size, which there are always factors of 2 in how you define that size, but the 1 over e squared radius is 0.7 microns. So it's Na of about 0.6.
What's the spacing?
Yeah, so the spacing in that picture was 1.4 microns, but when we do tunneling experiments, for example, then it's more like 700, 800 nanometers. And we actually, one of the things about these optical tweezers is when we do the tunneling experiments, then the atoms are close to each other, and we can't really quite resolve them if we were to image them. But then in real time, we take that entire array, and we go and we change the spacing. That wasn't a very good sound effect, but we change the spacing between something large and something small as a function of time. Okay. So in the experiments and those images that I was showing you, you have to do something that I refer to as parity loading. So you have to make sure that you don't have more than one atom in your trap, or else you wouldn't really have a single atom source, right? You wouldn't really know what you're initializing to. And so what's used to do this, again, was thought about early in the days of laser cooling and then in optical tweezers in the early 2000s, is if I am in a situation where I have a couple of atoms in these really tight traps, then what will happen is you can have what's called light-assisted collisions, where there's molecular states associated with the sort of S plus P situation when you have an excitation, an optical excitation in the system, and those can lead to very inelastic collisions, and if you have a couple atoms in the trap, they'll just go away. But if you only have one in the trap, then you don't get any of these light-assisted collisions, and then they stay, and then you have the single atom. And this works for sort of higher order as well. If you have 3, you can often go down to 1. And so it was shown that you could actually have this purple distribution here that corresponds to 0 atoms, 1 atom, but that you never see the 2 over here. So you can be very certain that you don't have 2 atoms, because these light-assisted collisions are very fast and just make absolute certain that you don't have more than 1 atom in the trap. Okay. And this is called collisional blockade. It depends on the volume of the trap, and it depends on the loading rate of atoms into the trap. So there are regimes where, for example, this blue is flattening out here, where you can see that you get to this 50% loading, where half of the traps are filled and half are not, and it's flat over some region where you can be sure you're in this collisional blockade limit. Okay. And you can even do fancier things. We're working on this in experiments now, which is that can I actually tailor these light-assisted collisions such that if I did have 2 atoms in the trap, is there some way in which I could not kick out both of them, but rather get to just the right spot where I kick out one and not the other. Okay, so I get so that their energy is very close to the trap depth. And one way that I can do that is these light-assisted collisions. If I tune red, I end up on this molecular state, and that gives off a huge amount of energy. If I detune blue, then I can actually tune the energy that is given off in this inelastic collision, or given to the atoms in the inelastic collision. And in that way, I can actually get histograms like this. I meaning the community. So there's a group in New Zealand who first was working on this, and they were able to show they could get 90% of the time they could get a single atom in the trap instead of 50% of the time. So we can also control things in that way. Okay, so in our particular experiments, one possibility is that given that we can control the position of the atoms, given we can control the filling of the sites, and also the motional states that I'll talk about in a bit, rearrange those atoms, in principle we can have a low entropy bosonic state that would, in principle, we could melt to a superfluid as well. In terms of this rearranging process, I'll just show some mini videos of the process to give you a sense of the time scales. So typically the traps are loaded, then atoms in individual sites can be moved over to where they want to be, where we want them. And so you can make different configurations that you might want to have. This is taking some atoms from a 3x6 array and then turning them into a line. That's one possibility. We can also in this, we're taking some atoms from the same array and then turning them into a circle. So in principle, you can create arbitrary configurations. Yeah.
So the implementation of these traps is like this crossing thing?
Mm-hmm. Yeah.
So does that mean that you have to move each row?
Yeah, right. So these images, I wasn't going to mention this in detail, but this is actually from our experiment where we do have 2 cross-DAO M's, but what we're actually doing is we're time averaging. So we actually flash the traps much faster than the atoms can tell. And in that way, we can actually flash between a really tight tweezer that moves the atoms around in any arbitrary configuration and a static array that does have this constraint of moving rows. Yeah. Okay. Yeah.
This arranging is one by one, or you could how many atoms can you
Yeah, I mean, that's a open question. This is about how many we can move right now. But
you did one by one, right? Like, so you just go and
oh, yeah. So in this picture, we are moving one by one. But actually, you can parallelize the moves. So in some experiments that we're thinking about, you could grab onto 5 atoms in a row and move them all over at once.
so
Is that?
besides arranging, I guess one could also think about your setup like as like a new way of driving your like putting energy and momentum into a system. I guess.
Yeah. Uh-huh.
One is,
Yeah, so I do think that dynamics is a possible, very interesting reason to have this system as opposed to, say, a quantum gas microscope where you might just start in equilibrium. And I'd say there's multiple ways in which this is relevant. Okay, so I think it's the spatial degree of freedom that you see in this picture, but it's also the motional state of the trap. And in principle, if we had the right control, we could actually start anywhere that we want there. Is that sort of the question, or? Yeah. Okay, all right, so yeah, let's talk a bit about the idea of if we just capture these atoms in these individual traps, and all of these pictures that you're seeing are basically of hot atoms. So they are at on the order of hundreds of microkelvin for some of those images, which is much hotter than ground state cooling. So what one has to do is, after you capture the atom, if you want to control the motional state, which all of the entangling mechanisms that I'll talk about, at least the second order, they depend upon the motional state. And so in that case, it's useful to be able to cool that motion. So in that context, let me just draw a quick schematic of how we do the cooling in our experiments. So if you imagine that we have the trap harmonic oscillator. Okay, and we have, if we think about using both hyperfine states, so we use f equals 1 and f equals 2. And we'll have to have a little more space to get up to our other state. So let's move this down a little bit. All right. So we have our harmonic oscillator for the motional states. And we're going to use hyperfine. So we have f equals 1, we have f equals 2. Draw the motional states there as well. Okay. And then we have way up here, we have our optically excited state in f prime. And what we can do is, let's say we start in this motional state here. We can drive an off-resonant Raman transition. So this is going to be called Raman sideband cooling for this reason. So we drive an off-resonant Raman transition that can take us down emotional quanta. And each of those steps corresponds to a different laser in the system. And those two lasers come in at different angles. So let's say we have a K1 associated with one of them, and a K2 for the other one. And so we can, if they don't come in co-propagating, then we have a delta K in the system. And then we can do this coherent transition over here. And then what we do in order to sort of cycle this process over and over again is we then optically pump and recycle over here, coming back to the ground states on the other side. So this is known as Raman sideband cooling. And some of the characteristic scales there, we have the 0-point fluctuations for the particular atom in the particular trap that we're using. So this is obviously the same expression we were using the other day when we were talking about these nanomechanical systems, where now the omega naught here is the trap frequency of these tweezer traps, and the mass is the mass of rubidium-87. So the mass is 87 AMU, and the frequency is about 100 kilohertz for these experiments. So for ion traps, the typical trap frequencies are about a megahertz. For these experiments, they're about 100 kilohertz. So an important factor, a dimensionless factor that comes into these experiments is called the Lamb-Dickey parameter. And that parameter is this 0-point motion times a k, which would be this delta k for this coherent transition that I was talking about. And so for our experiments, the 0-point motion is about 20 nanometers or so. The Lamb-Dickey parameter ends up being about 0.2. So Lamb-Dickey parameter is sort of a small expansion parameter as you think about this cooling. Okay. All right. So these are some actual data showing if we actually just pre-cool based upon a particular subdoppler cooling technique, then we can already start to see in these Raman sideband transitions an asymmetry between this guy here that corresponds to going down a quanta, and this guy here, which I would think of as sort of more the blue sideband transition, which would be going up. They're backwards because we're driving from f equals 2 to f equals 1. So we already have sort of n bar of a view with the pre-cooling. Another thing that you can see in these type of experiments is you can look at the oscillations of the carrier transition, and you can see they dephase if you're not actually in the motional ground state. To do the actual cooling, we pulse between doing this Raman transition and then recycling with this optical pumping. So first we do the coherent drive, we recycle, and then we do that over and over again. And then what we find is then we can look at the sideband asymmetry, and we can see that our red sideband has gone down significantly, and we think we're near the ground state we can also see the carrier transitions are more coherent. And if we look at the number for what is our three-dimensional ground state cooling, it typically is on the order of 90%. And that's really limited by this optical tweezer has a weaker dimension in the axial dimension, and that trap frequency is limiting us in terms of how well we're able to cool. But 90% is enough to do some of the experiments that I'll talk about. Okay. All right, so let's talk now about in a number of the experiments that we'll do, we'll actually have atoms tunneling between these different traps. So we start with our traps that are deep and far apart, and that's where we do this Raman sideband cooling. We sweep them down and pull them together, and we actually do this over a really large dynamic range. So it's a 20 megahertz trap depth to start with, and it's more like 20 kilohertz at the end. And so the atoms actually do stay cold over that whole range. So that's a statement of these optical traps can be quite stable. And then we might have the atoms tunnel between the traps, and then when we image, we always pin the atoms on the site at whatever point we want. And in any iteration of the experiment, we start with them far apart like this, and then this is sort of a movie showing how they go together and come back out again in any iteration of the experiment. Okay, so in all the experiments that I'll be talking about from now on, we're really just using two atoms, even though we're trying to get more into these experiments. And so in these experiments, we're often just loading with this 50% probability of getting an atom in any given trap. But we always see where that atom is before we start the experiment. And in that way, we have information that allows us, in some ways, that already removes entropy from the system. Okay. And so in all the data, we're looking at something where before tunneling, we see an atom in a particular place. After we do some experiment, we'll determine whether it's over here or over here. We can also watch, okay, and so we can see the atom tunneling. Here's the tunneling rate in our experiment, which is hundreds of hertz scale. And we can tune that tunneling by both changing the depth of the barrier as well as the distance between the traps. We can also retrieve this spin information. So we have our spin up and our spin down states. We can image those selectively at this point. And so we take actually one picture where we scatter a lot of light off of the atoms. And then when we do that, we scatter enough light, we make sure we don't scatter too much light so that we actually stay in the same cycling transition and so that we don't mix the spin states. Then we do a microwave pi pulse that flips those with respect to each other. Then we do the same detection, and then we're able to get information about whether we had spin up or spin down, or actually whether the atom was lost in the experiment. Okay. All right, so that's a lot of sort of nuts and bolts of these type of experiments. So the next thing I wanted to talk about is the equivalent of the Hong-Mandel effect for our bosonic atoms tunneling in these traps. And this will lead into one of the entangling mechanisms that I'll talk about later for creating a spin-entangled Bell state. But we can think about it in a variety of ways sort of early in this talk. So first of all, here's the abstract for the original Hong-Mandel experiment, and it says measurement of sub-picosecond time intervals between two photons by interference. So in the original experiment, so the Hong-Mandel effect is I have a beam splitter, and I have two photons that impinge on that beam splitter, and what I find is that I never get the 1-1 state out. And if that effect is very sensitive to whether those two photons impinge on the beam splitter at the same time. So they really thought of this as a way to get to that timing based upon this effect and not as a fancy quantum effect. In our experiment, there's sort of an analogy to this in the sense that this HOM effect is really a good way for us to diagnose our state purity, to diagnose how cold we've actually made our atoms. Even compared to the sideband spectroscopy, it's a very good metric to determine are both of the atoms in the ground state of this potential. Okay. And sort of, yeah, so in that way it's sort of determining whether we have what I call a single atom source, okay, instead of a single photon source. So let's go over a little bit more what the HOM effect is. Probably many of you have seen this in a variety of textbooks, but let's just go through it from the beginning just to identify the different notations. So let's just first draw the optical version. Where the first thing that one needs to understand in terms of terminology is what is a beam splitter and what does it do. So a beam splitter, I'll draw it as the optical object that has two ports, okay, so two input ports here and here. And if I put a single photon into one of those input ports to begin with, then what can I get out? Okay. Draw my output port slightly differently here. All right, so I'm going to get something out. I'm ultimately going to detect it on I'll draw photon detectors here. And if I put one photon into one port, then my input state I would write as 1, 0. And that is going to go to a superposition state of 1, 0 plus 0, 1, which, let's do that better. Okay, 1, 0 plus 0, 1. Now, this means that either the photon comes out here or comes out there. And that's a superposition of those two possibilities. This is often called a mode entangled state. So this beam splitter here, it's mixing modes. And to atomic physicists, this is odd in the sense that this is equivalent to applying a pi/2 pulse on my spin qubit over there, right? But in the context of these photons are spatially separated, this is often called mode entanglement. Just clarification there. Okay, so now let's say that we have two photons that are coming in. And then we also have two detectors to output here. All right, so what one finds in this case is this 1, 1 state goes to 0, 2 plus, or let me write it analogous to how I just did on the other plates. A 2, 0 plus 0, 2 state, okay, written in second quantization here. So it's a statement that I never get the 1, 1 state out. If I had two fermions that went in there, then I would always see the 1, 1 state, right? Polyblocking, I couldn't get 2 out of each port. All right, and so in an actual experiment, there's another color chalk here, then what you measure is a quantity called P11, which corresponds to, well, I'm going to call it P11. It corresponds to coincidence counts between those two detectors, right? So do I see coincidence counts? And what I see is that as a function of the position of this beam splitter, which is an experimental stand-in for are the path lengths the same, then at a certain position I will see this go to 0 when I only have this state at the output. Okay? And so in some ways, yeah, so this corresponds to in being able to detect this sort of relative timing in the context of that abstract. And in our case, it'll sort of correspond to the ability to make a pure state of these particular atoms that we're trying to control. Okay. All right, so I didn't say how that state came out. It's a very simple set of equations to write that out, so let's just write it out. And let's consider it now, thinking a little bit more in the picture of our two atoms in our two traps. So let's say that we have two identical atoms, and I'm going to draw 2 spin-ups to indicate that. So there's no other degrees of freedom in which these 2 atoms could be distinguished. And the possible outputs of the system I would draw like this. So I can either have okay, so this is what I would call my 1, 1, and this is my 2, 0, and 0, 2 options. And so if I think about the input state for a bosonic system, then I'm just going to write this in first quantization just because I can. So if I think of this as the initial state is symmetrized, okay, so that's my input state. And then what do I do to determine the output state? So the beam splitter mixes the modes, so this L goes to L plus IR. And the R goes to R plus IL. And I've put 1 and 2 to indicate sort of the particle numbers on there, but we don't really need to keep those subscripts. So this is sort of psi in, and then what is psi out? So I'll put a half here for all of the different prefactors of the thing that I'll draw inside of here. So we'll have left plus I right times right plus I left, and then we have to add that, and this plus is important here as to what happens. Then we have right plus I left and left plus I right. Okay, so if we go to all the trouble to multiply that out, what you'll find in this case is that the situations where we have the RL or LR terms, those are canceled because we get some negative signs, but the other terms don't, and we get 1 over root 2 R plus L. All right. So this state here, I would write in our other notation as this 2, 0 plus 0, 2. All right. And for the fermionic case, I get the opposite. I start with a minus sign here, and I end up with which I would think of as the 1, 1 state. All right. So did Manny Nil talk about some things related to how to understand states like this and the HOM effect? I saw one of his reading materials was sort of related. Not really? Okay. All right. I won't make any comments then. Okay. So let's see. In this case, P11, we expect it to go to 0. And in the fermionic case, we expect P11 would go to 1. And in the context of, let's say I had some distinguishing degree of freedom. So instead of starting with up, up, let's say I started with up, down. So in that case, I would expect that this would be just sort of like flipping a coin. And so I would expect a quarter probability for each of these guys, and I would actually expect P11 to be a half. Okay? All right, so that's all fairly straightforward there. And in our experiments, what we do is we have this beam splitter that is this tunneling effect. And what we can do is wait for the right amount of time for it to be a balanced beam splitter like I've been writing there. Yeah?
So the
Oh, sorry, yeah, yeah.
Come into play with the atom system? Like, where does that I physically arise? How does it?
Yeah, right. So why did I call it left plus I, right? Where does that phase come from? Yeah. Okay. So for the tunneling case, so now a phase is always relative, right? So I could do L plus R or L minus R or R minus L in the other way. So there's multiple ways I could do this. So I haven't. It's not the unique way I could write it, but in terms of yeah, I guess I would say that. We could probably go through it afterwards, but I think you're wondering, maybe one of the things you're wondering is, why is it analogous to the optical beam splitter, or go ahead.
There's a paper by Society that shows that this phase vector comes from conservation.
Oh, yeah, okay, sure. But that's a general argument. Yeah, for. Yep.
So the tunneling operator, yes. You have that destroy an atom on one side and the other. So you are applying, you start left, you are applying, it's a single atom, yes. So you apply an atom on the right, and you apply an operator that is destroy an atom on the right and create on the left. Is it to the I?
Yeah, so in that.
That is this time, this pi quarters when you have it's a pi half poles, and that's how you get the phase.
No. So I mean, any choice that I make has to obey that energy conservation, and I could have, yeah. Okay. So the beam splitter here in the atom case is you can see via the tunneling it looks like this, and in the case of this balanced beam splitter we have the reflection and transmission coefficients are equal. And then we can see in some data that we have these coincidence counts as a function of time, and the purple there is the distinguishable expectation, so this 0.5 limit, and then we can see that we dip below that 0.5. And we don't go perfectly to 0, so that means that we haven't created a pure state here. Okay. All right. So what else? So we can also vary the distinguishability by varying the spin here. And we have this, if we have the up-up state here, then we can get below 0.5. And if we actually have up and down, then those atoms will be distinguished, and we would go to this 0.5 limit. Okay? All right. So yeah, any other questions there? Yeah.
Can you imagine to scale this up and to perform some kind of Boson sampling?
Yeah. So the fidelity at which we're doing this right now wouldn't really work to scale it up, but we really do think that experiments can do better at the preparation, and so we think that it is quite possible that the boson sampling experiment could be done, with the advantage being that the detection constraints are at least different for atoms, right, in terms of what you could do for detection. Yeah. Okay. All right. So now let's talk about generating a spin entangled state. So the HOM effect, we're only mixing modes, and now I want to talk about actually creating spin entangled Bell states. All right. So one of the main ways that people are doing this these days is with an idea known as Redburg Blockade. So if you take your ground state neutral atom and you excite it to a Redburg state, then what you find is that you have a large interaction between your Redburg excited atoms. And that large interaction is fleeting because the Redburg state only lasts so long, but it's enough in order to get what's known as a Redburg blockade process. So given that strong interaction, if you have two atoms in some volume where their distance is such that the there's a large energy shift when they're both excited to the Redburg state, then you'll actually have what's known as a Redburg Blockade, where instead what you'll do is drive to a superposition of Rg plus Gr, where G and R are the ground state and the Redburg state. Okay. All right, and then what you can do is then you can remap that Redburg state to the ground state, and then you can create a spin entangled Bell state like this. And so this has been done in a variety of contexts, and also people are looking at many body physics that you can see when you do that interaction. So it can be very fast, but there are also some concerns about the ability to really control that Redburg state, though things are getting better and better. What I'll talk about sort of in more detail here is a spin exchange process. And in this case, we're using actually the ground state neutral atoms and looking at the on-site interaction of those two atoms and using that in order to create the entangled state. So let's talk about how we do that. So if we actually take two atoms, put them in two different spin states, those are the spin states that we're talking about over there. We put them together. Then we actually can think about this as being superposition of triplet and singlet states, and those will be spatially symmetric and spatially antisymmetric, obviously, and this is going to interact or be non-interacting for the bosonic case. This is sort of a textbook situation, and what you find is that you'll have an exchange process so that originally this up-down state will flip as a function of time. And if you catch that at the right time, then you can create an entangled state. And so in some ways it's nice in the sense that there's no engineering of a spin-dependent interaction. You just put the atoms on top of each other. It works for bosons and fermions. There's a lot of analogies, or this is basically a mechanism that's used in quantum dots. So in order to do all of this, we actually need to be able to start with the spin state that we want to start with. And so we start with two optical tweezers, an atom in each of the wells, and we put an additional addressing beam for this particular experiment. We shine that on one of the atoms. We can also do this by increasing the tweezer light in one tweezer and making it really shallow in the other tweezer. And we actually light shift a microwave resonance out of resonance so that we can only address the atom that's in orange. And in that way we can start with a state that's up-down. Okay, so if I take this situation and I tunnel via an adiabatic rapid passage process is the easiest way to get the atom over into the same site. Then I wait some time, and then I pull the atom back. Then what I find is that I can either measure spin up down or down up. And I want to keep track of what I measure as a function of a variety of parameters. So here we can vary the exchange time, the time that we're letting the atom sit on this particular well. And then we can see things oscillate from up down to down up. And if we stop at the right time, then we get this state here, down up plus I up down. And what we want to do is we want to characterize this state. And so one particular important thing, right, is that we want to know that this phase here is really what we think it is. Okay, so if I replace that in general by an e to the phi, is that phi what we believe it is? Can we rotate it and actually see something coherent going on? So in that sense, I could probably, let me just write down on the board in general what the idea is in order to determine that. So if I'm doing my experiment and I want to do the simplest things possible, and I were to just detect in any given run of the experiment, if I measure down or up, I will never find that I measure up, or down, down. I'll always measure either, the spins will be anti-correlated. In the sense I'll measure up or down. And I won't have a sense of this phase. So what is the way that people do get a sense of that phase? In the simplest way. I'll erase this. Okay, so in general, I have this state here, and now let's consider just two instances of that state. So say either the singlet state or the triplet state. So if I write okay, so that's an arduous process for something you already know. But the point is here I have a minus here and a plus here. And what is a way that I can extract in an experimentally sort of very easy way the distinction between these two? So one thing that I can do is I can apply a global rotation of the spin. So I can, for example, use microwaves to mix my f equals 1 and f equals 2, my two hyperfine states. Okay, so I have my microwave horn here, and I mix my up and my down states, and okay. Okay, so I'm going to mix up and down with a pi over 2 pulse, and so then what is going to happen? So if I do this, the singlet maps to singlet. This is exactly the same math as over there. Okay, so singlet maps to a singlet. The triplet though will map to another Bell state. Map to 1 over 2 Yeah, I'll just call that. Let's start simplifying this here. Up, up, plus down, down. Okay, so if I were to look at the what I'll think of as a parity measurement that tells us whether I'm getting up, up, or down, down, or some combination of ups and downs, that can actually tell me easily experimentally whether I had the singlet or the triplet state. And I'm only sort of belaboring this point because this is the way that we'll look at entanglement for all of our states. It's basically the way that people have looked at Redburg atom entanglement so far, and if you look at the first papers on ion systems, that's also what's done. Okay. All right, so just to draw just a very explicit chart of what one sees. So if I think about mapping to something I'm going to call, oh Jesus, I'm sorry, parity. Okay, so this parity will be either positive or negative for different spin possibilities. Right, and if I have the left spin and the right spin, and then I ask what parity should I assign for each of the possibilities. If I have the same spin, I assign a +1. If I have opposite spin, I apply a -1. Okay? All right, so when I make a plot that shows parity, that's what I'm measuring in the experiment. All right. So in the experiment, what I want to do is I want to rotate that phase, and then I want to use this metric in order to determine what that phase was as a function of rotating it. So I rotate it with a field gradient. I apply this global microwave pulse that mixes the spins, and then I can look at the parity as a function of evolution time, and I can see it oscillate between singlet that corresponds to a negative parity and triplet that corresponds to positive. Okay, so that's what I do, and then the amplitude of those oscillations is what tells me the important information. Okay. And here it exceeds some bound that has to do with the spin preparation that does tell us that this state is indeed entangled. Okay? All right. So let's talk about another way that we could imagine creating an entangled state. So again, what we're looking for here is to create a spin Bell state, and actually to use this mixing of modes that we talked about over here and ask, is there a way that we could get a spin entangled state out of that situation? Right, so if I only mix my modes with the beam splitter, then I end up with this state at the output. And you could sort of stare at these little diagrams for a moment and ask, if I were to measure a particular spatial configuration, let's say I always measured only selected experiments in which I measured the 1-1 state, right? Or I only selected experiments in which I measured the 2-0 state, then that would actually be a way that I could select out the spin state of interest. Okay? So there's an analogy to this in the context of polarization in optical experiments. And this is post-selected entanglement. And generally, if I have an atomic system and I do have interactions between my atoms, then it's probably better to use those interactions to create an entangled state. But on the other hand, it's sort of an interesting demonstration that we could actually do a post-selected entanglement experiment analogous to one would do in the context of photon experiments. So in photon experiments, what I'm drawing here is I have the orange and the blue, and those correspond to two polarizations in the experiment. And those two polarizations go into the beam splitter, and then I'm able to rotate individually what's going on in each of those two paths, and I'm able to detect at two different detectors down here. So we have bosons, two spatial modes, and then a polarization or spin degree of freedom. So we don't have interaction in this case, but we do have measurement in order to select out a particular situation. Okay. All right. So what is the atom analog to this? So the atom analog to this is I have two atoms and two wells that are separated to begin with, and then I bring them together and I allow them to tunnel between the two wells, and then I bring them apart again, and I also can do some things that I was doing in the experiments before, where I was, say, putting on a magnetic field gradient that allowed me to rotate one state with respect to another, and to characterize the state in the end. And what do I expect to come out? Well, I expect for bosons, if I have the spin singlet state, this would be associated with the 1-1 spatial state. And if I have the spin triplet state, this should be associated with the 2-0 or 0-2 spatial state. So if I do my experiments and I collect a bunch of information, but then I only analyze the experiments in which I see one atom in each well, then I could characterize this state in the same way that I was talking about there and see if I also see entanglement in the system. Okay? All right. So everyone's okay with post-selected entanglement, and that seems legal? Okay. All right. So what we can do is the same thing that we did before, where we apply this global microwave pi over 2 rotation, and then we measure this parity. So the same parity that I was talking about over here. So -1 will correspond to the case where I have spin singlet, and the +1s will correspond to the triplets. Okay. All right, so when we start the experiment and we haven't introduced this beam splitter that mixes the two modes, then we see that we have an equal mixture, singlet and triplet, but then we start to create the singlet state if we rotate into a situation the tunneling time is such that we have a beam splitter. Okay. And then we can do the same thing as before, where we apply a magnetic field gradient that differentially rotates the up and the down. Now, I didn't mention how we do this. So we can do this either with a real magnetic field, or we can do this with a fictitious magnetic field that's actually created with the laser light. So we apply this magnetic field gradient. And then we do our global microwave pulse, and then we see this parity oscillation, and we can see it's larger than a bound here that again corresponds to our initial preparation. And we find if we don't do the tunneling, then we don't see oscillations in that parity. Okay. The fidelity in all these experiments is basically limited by the state preparation. So it's limited by things like that we don't cool the atoms all the way to the ground state, and it's also limited in these experiments by how well we prepare the spin. Okay. And so it's quite finite at the moment, but we think there's room for improvement. Okay. All right. Any questions about that? Yeah.
So when you adiabatically move these tweezers, does that induce heating of the atoms at how much?
Yeah, so actually moving the tweezers, we actually think is a negligible component of our problems. Yeah, so there is a finite heating rate as a function of time just sitting in the trap, but the motion seems fine, as long as it's adiabatic. Yeah.
So when you post that to the case where you have two atoms in each of the trap, how to decide there are atoms there without changing the spin states of these atoms?
Yeah, right. So in these experiments, well, first of all, it's all destructive in the sense that it changes the motional states, and the imaging where we can preserve the spin is actually. So do you mean just that we can spin selectively image, or that we don't destroy the?
Yeah. So because for trapped ion, if you want
Mm-hmm.
to detect so you want to if you use laser to see the to drive this ions, you will change the internal state of these spins. So for this cold atom, where if you want to know if there are atoms there, will this laser change the internal state?
Yeah, right. Okay, so the imaging process, there's actually two different procedures we can use. Some of them do completely mix the state, and some of them don't mix the hyperfine state. So there's actually one process that we do where we just cool simultaneously and gather a lot of photons, and that mixes them completely. In this particular experiment, we were actually using a different technique, which is actually to very quickly collect a small number of photons on the cycling transition before it decays, right? And in that case, we do actually preserve the spin. Yeah.
So maybe I missed it, but is there any problem with the collection efficiency that limits you here, or?
So no, the collection efficiency doesn't limit us in the sense that, I mean, compared to other infidelities, the fidelity at which we can determine whether we have an atom there is fine at the sort of collecting 10 photons level, which we can do when we just scatter enough to look at the particular atom. But that's a statement of we have other things that are limiting us sort of more than that. Yeah, in sort of these quantum gas microscope experiments that you saw the images of early in the talk, there you're scattering sort of, many thousands of photons off the atom because you're allowing cooling to happen at the same time. So you can get large signals. Here, since the atoms are far apart, it's also sort of the limits that are relevant for ions in terms of how many photons you need to collect are also what's relevant here. Okay, so I think that, what else do we have? Okay, yeah, I was going to talk about a few further reading type things, but in terms of where we're going from here. So I think that the neutral atoms, there's a number of different aspects that we can look at. I think one future thing is sort of larger number analogs to sort of photon type problems like boson sampling was already mentioned. There's sort of larger scale non-equilibrium spin physics type things that we've been talking about with Anna Maria in terms of what one could simulate. And then there's the idea of how good could a quantum logic gate be for neutral atoms. And I think that the Redburg systems are getting interesting from that perspective. The experiments that I showed you, I think, are sort of useful thought experiments about how one gets entanglement with ground state atoms, and in the case where we have to symmetrize bosonic or fermionic states. But they do depend upon motion, and in general, the ion trap community found, well, anytime we try to use motion as the important thing that's holding onto our quantum information, that's not such a good idea, right? And so maybe there are ways that actually you could do things with ground state atoms where you could have insensitivities to the motion. That might be interesting to look at. And certainly we can imagine cooling these atoms a lot better and getting into a regime where we can study some amount of many body physics with some set of atom traps. Here's a few references that might be relevant if you want to look into this more. So the first paper there is actually, they benchmarked how good of a sort of single qubit rotations can I get with trapped neutral atoms that are that are addressable. And so that says something about where the sort of single qubit rotations are, which in general should be able to be just as good as ions, right? In the sense that they're isolated atoms. And it's really with neutral atoms, it's more about how do you get the interaction that you need in order to do, say, a 2-qubit gate. There are a number of experiments that look at entanglement, not only in these tweezer traps, but also in the quantum gas microscopes. So in Marcus Reiner's group, they've looked at entanglement entropy, which is sort of it uses the HM effect, except for you're interfering 2 larger scale samples instead of just 2 atoms. This topic here, this paper by Maltatishi, Essential Entanglement for Atomic and Molecular Physics, I find it sort of a useful benchmark for translating language between the photon world and sort of the atom world, if you care about or you come from either of those worlds. And it's sort of thinking a little bit about how do I understand symmetrization and its relation, and if I'm trying to characterize how much entanglement do I have, how do I deal with that properly? And then this is a paper that some of the data that I was talking about came from. All right. Okay, and then these are the folks that have been taking the data that I showed today. Here's my optical tweezers, optomechanics, and I think that I'm a little early today, but we can talk more, or people can go to lunch. So, yeah. Yeah.
Can you comment on how to use these to create like a cluster state or other states?
Yeah, so I mean, I think that I can't talk about general algorithms that I've sort of fully worked through, but I can talk about sort of the ways in which I think it might be possible to have a fair amount of flexibility on sort of what atoms are talking to what other atoms. I mean, because you really, I think you can move these atoms around without sort of crosstalk with other atoms. I think it is quite possible to take this atom over here, have it interact with this one, and then move back over here. And so I think in that sense there could be pretty unique architecture somehow that come along with that. It's certainly, it's quite different than, well, it seems like those pictures look an awful lot like a chain of ions. How you control them is really quite different. I don't know if that answers the question, but yeah.
You're saying cluster states?
Yeah.
But I think most of, instead, I think the simplest interaction that we have is S.S. So it's not going to be exponential swap gates that we do here. So because, I mean, on-site contact interactions are S.S. So I think that giving the easiest way to create these swap gates when you have two particles in the same side.
Yeah.
And like Emmanuel, I mean, you have two particles in the same side, super exchange. I mean, take two particles in the same side and separate them. But if you want to have like a Z-square type of interactions that you need for clusters, one possibility that we can use is that use kind of a string or recoupling in the sense that you can apply a phase of the phase of the laser can depend on where you are.
Yes.
And when you have this type of phase dependence, you can tweak your interaction instead of S.S. You can do anisotropic terms and change the interaction, or you can use to make the tunneling state dependent,
Yes.
and then you can also change the shape of S.S to something different. I don't know if this.
Can you do like a spin-dependent tunneling for this experiment?
Yeah, in principle, one could use those same techniques. Yeah, so you can detune to between the D1 and D2 line, just like you do in lattice experiments. Though I think is the spin-dependent tunneling, would it be? I always wonder if some of these abilities to sort of move atoms around could compensate for that in some way, in terms of often the reason you want to do that. Well, in the sense that you want that for the orbital interaction.
Well, if
Yeah.
you want to break the symmetry, you can do something.
Yeah, no, that's true. Yeah. So, but in that context, the optical trapping control and the control of the internal states of the atoms is the same as when that's done in lattices. So, yeah. Okay. All right. Thanks a lot.